Hello. This is a video on applying similarity and proving the Pythagorean theorem. Okay, I'm using the Smart Notebook tonight, and hopefully this will work. Let's get right to the proof of the Pythagorean theorem. And let me see if I can go full screen here. Let's see. Okay. So this is going to be a proof of the Pythagorean theorem. We have triangle ABC and right angle C. The legs are A and B. We usually use lowercase letters for lengths of sides and uppercase letters for points and angles. Also, it's typical that lowercase a would be opposite angle A, lowercase b is opposite angle B, and lowercase c is opposite point C. That isn't always the case, but it's typical. Our hypotenuse is C, and we're trying to prove that a squared plus b squared equals c squared. So we're going to start out with our given. So you should write that down as your first statement. Pause the video as needed. Now, let me give an overview of the proof here. We're going to be dropping an altitude from the right angle to the hypotenuse down here to point D. And this is going to form three right triangles, and all three right triangles are similar. The left-hand triangle, the right-hand triangle, and the big triangle. Also, the hypotenuse here, side C, is now broken into two pieces, X and Y. So let's see what our next line of the proof is. We're going to draw an altitude from C. It's going to be called segment CD, and the reason for this is through a point, not on a given line. There is one line perpendicular to get to the given line. I am going to need this fact later on. X plus Y equals C. That's the segment addition postulate. The segment addition postulate was discussed in the comments on reasons, which was in week 6. Now, proceeding, we need to get ready to prove the three triangles are similar, and we're going to use angle. Angle B is congruent to angle B. This angle B is an angle in the left-hand triangle, and it is also an angle in the large triangle. In a similar manner, angle A is shared by the right-hand triangle and the large triangle. Reflexive property of congruence. Line 5. These angles down here at D, angle CDB and angle CDA are right angles. Definition of perpendicular. Perpendicular lines meet at right angles. So we have two right angles down here. We have the right angle up at C, which is given, and these three angles are congruent. Angle C, oh, this looks like a typo. It should be CDB. Angle CDB is congruent to angle CDA is congruent to angle C because all right angles are congruent. The right angles are congruent, the angles at B are congruent. That's enough to get similar triangles. The left-hand triangle, triangle CBD, is similar to triangle ABC, the large triangle. Notice the corresponding order of the letters, which is important. I'm starting with the small acute angle. Then I'm going to angle B, which is kind of the medium-sized angle, and my third letter is the right angle. And the same thing here. This is by angle-angle similarity. In the same statement, I have the right-hand triangle. Triangle ACD is similar to triangle ABC. So now I can set up my proportion. I'm going to be setting up a proportion, and I'm going to be using the letter A twice. In one case, I'm going to be using the letter A because it is the hypotenuse of the left-hand triangle. And I'm also going to be using the letter A because it's the short leg of the large triangle. Let's take a look. X over A equals A over C. X over A, this is short leg over hypotenuse in the left-hand triangle, and A over C is short leg over hypotenuse in the large triangle. In a similar manner, I'm going to be using the letter B twice. And of course, the reason we want to use the letter B twice is so that when we cross multiply, we get B squared and A squared because we have our eye on the prize. Y over B equals B over C. This is a longer leg over the hypotenuse equals the longer leg over the hypotenuse in the large triangle. And the reason is corresponding sides of similar triangles are proportional. It's kind of like CP-CTC, but it's not corresponding parts of congruent triangles are congruent. Its corresponding sides of similar triangles are proportional. Now we're going to be doing a bunch of algebra. Cross multiply, we get A squared equals XC and B squared equals YC. And maybe you can pause the video and anticipate what we're going to do with these two equations. Once again, keeping our eye on the prize. Yes, we're going to add the equations. A squared plus B squared equals XC plus YC. Once again, I encourage you to try to anticipate the next step because this proof flows very logically and very naturally. There's a common factor of C, so we're going to factor that out. So we have A squared plus B squared equals C times the quantity X plus Y. That's also algebra. If we wanted to get technical, we could say the distributive property, but that's not our emphasis here. So we'll just say algebra. And once again, you can probably anticipate the next step because X plus Y is in fact C. We see that here. So what I do is I remove X plus Y and I put C in its place. C times C is C squared. So my last line of my proof is what I'm trying to prove. A squared plus B squared equals C squared. And that's by substitution using line 3 and line 11. Now that we've proven the Pythagorean theorem, I would like to take a look at a few more theorems, and I'm going to take a quick look at the book, section 6.6 and 6.7. So here we are at our textbook, and chapter 6 is on similarity. By the way, I will make the comment that we're primarily using angle-angle triangle similarity. You can prove triangle similar with side angle side and side side side, but we're not going to be using those. 6.6, theorems involving similarity. Here we have three theorems. The Triangle Proportionality Theorem, which you want to take down in your notes. A line parallel to one side of a triangle divides the other two sides of the triangle proportionally. The Triangle Angle Bisector Theorem. The angle bisector of one angle of a triangle divides the opposite side of the triangle into segments proportional to the lengths of the other two sides of the triangle. Very interesting. And of course, the Pythagorean Theorem. For a right triangle with legs A and B and hypotenuse C, a squared plus b squared equals c squared. There is one more theorem that we're going to be doing here this week that is not in our textbook. They do have a nice video here of the proof of the Triangle Proportionality Theorem, and you're welcome to look at that, but I will be proving it. And my proof will be very similar to theirs. The idea of the Triangle Proportionality Theorem is we are going to be looking at the pieces along the sides here that are cut up. So BD is this little piece here over AD, which is this piece, is equal to EC over AE. We'll be looking at that in greater detail. Once we have that, then we use that to prove the other theorems. And they have lots of nice examples here. Now I'd like to look at section 6.7 on applications of similar triangles. And they have a video here about finding the height of a tree. And it's very typical that we would use similar triangles to find unknown heights and using shadows. Michael's shadow is proportional to Michael's height. The sister's shadow is proportional to the sister's height. So we can set up a proportion. Michael's height over sister's height is equal to the length of Michael's shadow over the length of the sister's shadow. This particular proportion here would be called a between proportion, because to set up the fraction, we're going between the triangles. It would also be correct to say Michael's height over Michael's shadow equals sister's height over sister's shadow, and we would get the same answer. Now I would like to look at a proof of the Triangle Proportionality Theorem, and you should have a handout for this. So we have triangle ABC. This is our larger triangle here. D happens to be on this side, and E happens to be on this side, and segment DE is parallel to segment BC. We have a segment cutting through the triangle that is parallel to one of the sides. And we want to prove that DB over AD is equal to EC over AE. As I mentioned in suggestions for doing proofs, it's very important to become very familiar with the proof statement so that you know what the goal is. Keep an eye on the prize, so to speak. So, of course, we start with our given. We are going to be using similar triangles here, so you might try to anticipate how to get the similar triangles and what the similar triangles are. I have angle 1 congruent to angle 2 and angle 3 congruent to angle 4 because these are corresponding angles. Notice that these are not alternate interior angles, they are corresponding angles. And we're going to be kind of lenient on that rule. You could write out the full version. Parallel lines cause corresponding angles to be congruent, but this is sufficient. We have two pair of congruent angles, so therefore we can state the triangles are similar. Triangle ADE is similar to triangle ABC by angle-angle similarity. Proving triangles similar is quite easy. Then we set up our proportion. And this is the entire sides of the triangles. This is not the pieces yet. AB over AD is equal to AC over AE. Again, pause the video to convince yourself that that is true. Our reason: corresponding sides of similar triangles are proportional. I am going to want to break this up into pieces, so I use the segment addition postulate on these sides. AB is equal to AD plus BD, and AC is equal to AE plus EC. Segment addition postulate. I hope that this is obvious. If you think about it, it should be clear. Now I substitute. I take out the numerator here, the AB, and put in AD plus BD. I take out this numerator and put in AE plus EC. This is substitution line 4 and 5. Once again, a very natural flow. Maybe you can anticipate the next step. I'm going to break this into two fractions on the left-hand side and two fractions on the right-hand side. This is how we add fractions. AD over AD plus BD over AD equals AE over AE plus EC over AE. That's algebra. That's how you add fractions. But what's AD over AD? And what's AE over AE? Yes, these are 1. A number divided by itself is 1. That's algebra. And then I'm going to just simply subtract 1 from both sides of the equation, and I'm left with what I was trying to prove. Part DB over part AD is equal to part EC over part AE. And the reason is that I subtracted 1 from both sides. This is a very nice example of how we build mathematics. We have similar triangles, which has to do with the lengths of the sides, and we prove a theorem that has to do with pieces. And now we're going to use the Triangle Proportionality Theorem to prove a more general theorem. This is called the Parallel Projection Theorem. The black line is needed for the proof, but it is not part of the theorem itself. So for right now, ignore the dotted black line. Let's take a look at the statement of the Parallel Projection Theorem, which you'll need to take down in your notes. On any two transversals, parallel lines cut off segments whose lengths are proportional. This is quite a powerful theorem because it is very general. We have a series of parallel lines, line AD, line BE, and line CF, and we have any two transversals. And we have some segments on this transversal. We have AB and BC, and we have segments over here on this transversal, DE and EF, and they are in fact proportional. This is quite a short proof. We start out with our given information that we have parallel lines. By the way, sometimes a set of parallel lines are called a pencil of parallel lines. I'm not quite sure why the term pencil is used, but it is. Then we draw in segment AF. And what segment AF does very nicely is it forms two triangles. And we're going to be applying our previous theorem. We're going to be applying the Triangle Proportionality Theorem to this triangle ACF and we're going to be applying it to this triangle FDA. So the reason number 2 is 2 points are contained in one line. This blank is one line. Now let's take a look at line 3. AB over BC equals AG over GF. What's the reason for line 3? The reason for line 3 is the Triangle Proportionality Theorem. And furthermore, DE over EF is equal to AG over GF by the same reason, the Triangle Proportionality Theorem. This is statement 3. But these are both equal to AG over GF, so I can substitute and we get exactly what we want. The final theorem I'd like to look at is the Angle Bisector Theorem. Let's take a look at this statement. Once again, the black line is part of the proof, but not part of the theorem itself. We start out with a triangle ABC, and we have an angle bisector. The statement of the theorem is as follows. The bisector of an angle of a triangle divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So the opposite side here is going to be divided into segment BD and segment DC. If we look at our proof statement, these segments here, BD over DC, as a fraction is equal to AB over AC. So let me see if I can think of an example. So let's say that these sides are 20 to 30. So it's a 2 to 3 ratio. These sides here would also be in a 2 to 3 ratio, but they look like they're a little bit longer. So let me see if I can make up some numbers that might work. Maybe this side AB is, for example, 32. AB over AC needs to be in the same ratio, 2 to 3. So it's basically 1.5 times. So if I do 1.5 times 32, that's going to add on half, which is 16. This will be 48. So this is an example. This is just an example. It is not a proof. Now let's see what the plan for the proof is. First thing we're going to do is draw a segment CE that is parallel to segment DA. And that's legal because through a point, not on a given line, there's exactly one parallel line parallel to the given line. And of course, the reason we're doing this is so that we can use our Triangle Proportionality Theorem. And then I extend this side AB to get point E. So this forms a nice big triangle that I can use my theorem on. Now something very interesting happens. We have parallel lines here. EC is parallel to AB. So this angle here at A is congruent to this angle at E by corresponding angles. So I can put a single mark here. This is congruent to this by corresponding angles. It's also congruent to this because of the given. But also, if we use this as a transversal for these parallel lines, this angle and this angle down here are alternate interior angles. So this one also gets 1 mark. So we have 4 angles that are congruent. Now, if we look at triangle AEC, it is an isosceles triangle because we have 2 angles that are congruent. So that means this side is congruent to this side. Then we set up a proportion here using, once again, our triangle proportionality theorem. Let's see if we can set up that proportion. So we have BD over DC is going to equal AB over AE. And now I'm just going to substitute. AE here is equal to AC. So I'm going to substitute that into this position. AE is equal to AC. And this is what we're trying to prove. This is not a complete proof, but it's the idea of the proof. The last thing I'd like to do is take a look at some notes on what is proportional and what is not proportional. So this is our other handout. Let's assume that we have triangle ART similar to triangle ABC, and we won't worry about why they're similar. We'll just say that they're similar. Maybe we have some right angles in a common angle. That's not the issue in the point that I'd like to make now. We have lots of proportions that we can set up. First of all, in our first box, we can set up proportions using corresponding sides. AR over AT. I'm sorry, I read that wrong. AR over AB is equal to AT over AC. This is a between proportion because AR is in this small triangle and AB is in the large triangle. AT small, AC large. I'll let you read the second one on your own. The third proportion that I have here from the similar triangles is RT over AT is equal to BC over AC. This is a within proportion because on the left-hand side, the two segments come from within a triangle. And the right-hand side, the two segments come from within one triangle. By the way, this is slope. And this is why fractions and proportions and similar triangles are so important, because slope is so important in linear functions. Now, if we move to our next box, we're not going to be setting up a proportion using sides of triangles, but we're going to be setting up a proportion using the Triangle Proportionality Theorem. AR over RB equals AT over TC. Notice that TC is not the side of a triangle. Now, AT could be thought of as a side of a triangle, but in this case, it's part or a portion of a triangle that was divided by the parallel line. Now for the caution. Now for our big caution. You cannot mix in your proportion sides of triangles and partial pieces of sides of triangles. AR over RB would be pieces. RT over BC are sides of triangles. These fractions are not equal. This is not a proportion. I hope you have found this video to be useful and helpful. Have a great day.